Today we start the topic of buckling, and buckling is distinctly different than everything. Buckling is distinctly different than everything we've done so far. So far, we've had a load applied, and then the deformations are proportional to that load, linearly proportional if we're in the elastic region, right? Well, today we're dealing with buckling, which is a phenomenon where rather than the material strength being the concern, it's the material stability being a concern. And so then our deflections are not necessarily linearly related to the load applied. For a, I don't want to say small load, but for a certain magnitude of load, we might have excessively large deflections. When I say buckling, do you have kind of an intuitive sense of what buckling is? What's your just general knowledge of buckling?
I think about where your leg buckles under you.
Okay, so you're standing here and then your knee juts out. Good. That's kind of what everyone thinks of. You think of a member in compression. Maybe you didn't think of it specifically in compression, but that's what it is, right? Your leg is in compression. And then it experiences a transverse deflection or a lateral deflection, even though your load is being applied vertically. That's typically what we see that tells us that buckling has occurred. But I want to give you a definition of buckling that is a little bit more theoretical than that. And people, very few people will use this definition, but I want you to have this definition. Just because very few people know it doesn't mean it's not true. Okay. Buckling occurs when a compressive axial force causes a member to become unstable. Now, when I say unstable, I don't mean deflect laterally. I mean unstable. And what I mean by unstable, do you know what the word unstable means? I'll draw you some pictures. This is what I mean by unstable. I have a valley and I have a hill. And I place a ball in each. Which of those do you think is unstable? The hill. The hill looks unstable, right? Because what happens when I move the ball in the valley to a new location? It goes back. Perfect. And what happens when I move the ball on this hill? It's gone. It's not going back to its initial configuration. So this is what I mean by unstable. This is unstable. This is stable. Unstable means that if you displace it from its initial configuration, it will not return. And in fact, not only will it not return, it's probably going to experience excessive deformations that you did not intend. But if I have this ball sitting at the crest of this hill and I don't move it, it's still unstable. Because I know that if I did move it, it would roll down the hill. Do you see that? It doesn't necessarily have to roll down the hill for it to be unstable. And when an axially loaded member experiences this large deformation, so say we have this axial load and we displace the member like so. So we displace it by some small delta. So delta small. And what's going to happen is if it's unstable, instead of it returning to its initial position, it's going to grow to be some large delta. And in fact, it might even snap in half depending on the loading and the material. So stability is a measure of whether a member that is deflected will return to its original position. The transverse deflection does not necessarily occur, but if we see that, it's a common visual indicator that buckling has occurred. And this deformation, like I said, is not proportional to the load applied. Stability, whether or not a structure is stable, is going to depend on the ratio of the disturbing moment to the restoring moment. So that the loads are going to be causing some moment on the deformed shape. In the initial configuration with axial load, there's no moment. If we assume that it deflects, right, we apply some deflection to it, now our load will cause a moment. So for example, if we have a column with a pin support and we attach it to a spring, that spring is attached, spring is attached to a wall, and we apply a load. Initially, there's no moment. This is load perfectly balanced on this member, but we want to know if it's stable. And so the way we figure that out is we displace it. We take it over here. Our load remains on top. Now we have some delta that it's rotated, which means that spring has to extend. So now that spring has a force equal to K delta. And we're trying to figure out, or what we want to know is if this is, in order to determine if this is stable, we have to determine whether the moment that is causing the disturbing, so that would be the moment created by this load, is that larger than, less than, or equal to the moment of the spring trying to pull it back into place. That'd be our restoring moment. So mathematically, we could take the sum of the moment about, let's call this A. We know that it has to be equal to 0 if it's going to be in equilibrium. And the spring, the restoring moment, is the spring constant K times delta to give us the force. That force is going to be acting to the left. It's going to be trying to pull that spring back to its initial position. So that force gives us a positive moment, and it needs to be multiplied by the length L. Now let's assume that this is a small angle, so small theta. If that's the case, what is delta equal to?
Theta.
Is it theta? Or is it L theta? So let's see, if we have this triangle, let's say the member itself had a length L, and this is a small angle theta. I want to know this dimension delta, and it should be L sine theta, which is L sine of a small theta is theta. So you were going straight to the sine theta, but don't forget we need to multiply it by the hypotenuse dimension. Good. So that moment ends up being K theta L squared. Now our disturbing moment is going to be a negative moment, and it is whatever our load is, so we'll call that P, multiplied by that same delta, which is theta L. And that gives us our moment. So another way we can write this is pull out the L theta from both terms. And then we're left with KL minus P. Therefore, KL equals P. So if KL equals P, then it's in equilibrium, which means we can displace it and it'll actually stay in that displaced configuration. So it's not unstable, but it's on the cusp of becoming unstable. Or I guess maybe it is unstable actually because it didn't return to its initial position. But so this will stay in the deformed location. So that's kind of our equilibrium. But if we were to increase even slightly the spring force, our restoring force, so if KL is greater than P, now this is stable and it's going to return to vertical. Of course, it'll oscillate a little while, but eventually it's going to end up vertical again.
What is P again?
P is the load applied. And similarly, if KL is slightly less than P, so we increase our load to be just slightly more, now it's unstable. And what's going to happen is that it's going to try to reach equilibrium. So it's going to say, well, the negative moment is larger than the positive moment, therefore I'm going to accelerate to the right. It'll move a little bit more. I shouldn't say right, to the clockwise. It'll move a little bit more, but now the restoring moment is even smaller compared to the disturbing moment. So it's going to keep going, and then it'll say, oh, now my disturbing moment is even larger and even larger. The more I move over there, the larger it gets relative to my restoring moment. And so it's going to kind of run away. You might end up in some, based on the geometry, you're going to end up with some large angle, in which case this assumption is no longer going to apply, and you might end up in where it comes to an equilibrium position. Like maybe your spring is stretched out here and it ends up hanging here. Otherwise, it might go all the way down and hit whatever the floor is. So another question we need to think about is, which direction, if it does deflect laterally, which direction does it go? So if I have X and Y coordinates, and I place a load P on this member, then, whoops. And then we say the base is, let's say, fixed. Will it bend about the y-axis? Sorry, will it bend about the x-axis or about the y-axis? Okay, and why will it bend about the x-axis? All right, so what I think you're getting at is that its resistance to bending about the x-axis is lower because the height measured perpendicular to the x-axis is a smaller value than the height measured perpendicular to the y-axis. So if you have something like this, not that I want to ruin my book binding, but if you have a book like this, it's easier to bend it about this weak axis than it would be to take it and bend it. I can't even bend this book about the strong axis, right? So if I'm putting a load on it and it's going to deflect in whichever direction is easiest. And so that's always going to be about the weak axis. You do this 100 times, it's never going to deflect the strong way, right? But what if I have a square? We could choose? Who can choose?
No, I said pick and choose.
Pick and choose. Is that your way of saying it's arbitrary?
Like, yeah.
Yeah, so at this point, like you said, if you have the material being non-homogeneous, or there's maybe some imperfections in the density of the material, that might be enough to influence it to deflect one way versus the other. But other than that, it's somewhat arbitrary. That mathematically, it's the same whether it deflects about the y or about the x. So either is equally likely, may be influenced by, could be influenced by the load. If you don't have your load perfectly centered, that could cause it to deflect one direction. If it's creating a very small moment about one of the axes, that might be enough to influence to always deflect that way. Could be that the geometry is not quite perfect. They told you it was a 4x4 column, but it's really a 3.98 by 4 column. That could be enough to influence it. Or maybe there are material imperfections. Like I said, previously, if perhaps there's some pockets of voids in the material, it's not quite homogeneous, that might make it weaker in one direction versus the other. Okay, but what if this is perfectly symmetrical? The geometry is absolutely perfect. We have a circle. At every point along that circle, it has a perfectly equal radius to every other point. And what if it's perfectly homogeneous? There are no material imperfections. And what if our load is perfectly centered? Now, which direction is it going to deflect? Exactly. In theory, if we can make the situation perfect, we perfectly balance our load at the center, it's perfectly symmetric cross-section, perfect homogeneous material, there is absolutely nothing that requires it to deflect. It could simply compress. And mathematically, there is a solution that, in fact, the most basic mathematical solution says that it doesn't deflect. And so as you're going to see in our coverage of buckling, in order to determine the load at which it deflects, we have to actively choose to make it deflect. We have to assume that it did deflect. You can't directly calculate the load because there's always an option that says, I stay straight. And so you can never really get to that answer directly. You have to choose that you went down that road and then backtrack the load that caused you to end up there. Good, that's a really important theoretical point. I want you to know that. If you go to grad school, I want you to know that. If you apply for a job as an academic, I want you to know that. If you're living and working in the real world, it's not so important, right? Because when have we ever built something where the loading was perfectly centered, the material was perfectly homogeneous, and the tolerances on that material were such that the geometry was absolutely symmetric? Pretty much never. So that's why we see the deflection happening. But mathematically, it's not a necessity. It doesn't have to happen. You can buckle something without it deflecting. What that means is the minute you come over and tap it, it's going to collapse. And so this is a really concerning, somewhat of a concerning failure mode, because unlike, say, yield stress, you don't really see this happening. Everything looks great until it's not great. Okay. So I want to do an example. We have a beam that's pinned over here on the side. It has a support here. That support attaches to a column. It's a rigid column that has a spring at the base. So just like axial springs, where the force is K delta. So if you have axial spring, force is equal to K delta. You can have a moment spring where your moment is equal to, make it beta. Beta times theta. So the amount of rotation multiplied by some stiffness gives you your moment, restoring moment. And let's say that this beam is loaded with a distributed load, W, and I want to know what the maximum load is, or what is the load on that beam at the time that that column becomes unstable. So how might you suggest we start?
Is that a spring that's going into the board?
It is a spring that is based on the rotation about an axis going into the board. So as I cause that column to rotate in the plane of my screen, the moment that that spring tries, the moment with which it tries to restore the situation is some constant beta times the amount of rotation in that plane. All right, take a moment about a point. Do you have a particular point you like to take the moment about? The spring, that's a very good choice, absolutely. Now, are we going to take the moment in this configuration, or do we need a different configuration? We need a different configuration, good. So I'm going to assume, do you care whether it deflects left or right?
Right, so it's positive.
Okay. So we're going to assume that it deflects like so, which means I have, if I redraw this, I have this deflected member, I have a spring, and I have theta, and we have some length of that member. So we're going to take the moment about the spring. Oh, and I forgot the most important part, the reaction from that beam. What is the magnitude of that reaction? Let me give you that this is 6 meters. You know what? I don't really feel like having any numbers today. Let's make that a little low.
So the spring is the thing that the distributed loads on?
This is a beam. The distributed load is on a beam. The beam is supported by a column whose base has a spring. So it's not quite pinned. Pinned would mean that it could rotate freely, but it's not quite fixed, because fixed would mean it couldn't rotate at all. Instead, it has some resistance to rotation, which is really a more accurate representation of a structure.
The spring's
Yeah. Do you know what a chip clip is? You eat the whole bag. You don't save it. Okay. No, yeah, like a little clothespin. There we go. You know what a clothespin is? Okay, good. Well, a chip clip closes the chip bag.
okay.
Maybe I just call them a chip clip. But anyway. But okay, clothespin. You know how a clothespin works, but I don't think a clothespin works like this. But do you know what I'm talking about when I say there's a little plastic thing in your kitchen that when your mom says, put away the chips, you've eaten enough chips, you put it back on. And there's a spring in it, right? And it's kind of a coil. That is exactly what I'm talking about. I took one of those and I put it at the bottom of a column. And so now it can kind of rotate, but it requires more force to make more rotation. Okay, so what is the magnitude of this force acting on our column? W little l. I need one more thing. Nope. Okay, let me back up. I have a beam. That beam has distributed load. What is it? Thank you. WL/2, right? Yeah. The reaction here is WL/2. That then becomes the load on our column. Now that we've done that, we don't need to worry about this beam anymore, okay? So now the sum of our moments, the disturbing moment creates a negative moment. So we'll say negative WL/2 times big L theta. That's the amount of this horizontal displacement. The spring wants to restore the situation with a moment that's equal to a constant beta times the amount of rotation. So L theta. The things that are in both terms aren't going to be of much consequence because I'll say this is equal to 0 to put it in equilibrium. And so I can go ahead and cross out L and theta. And what I get is that W equals the spring constant beta times 2 over the length of the beam. Is that right? So the shorter that beam is, the more load I can put on it. It kind of makes sense, right? And it's of course going to be a function of that spring constant. Okay, I have one for you to try. Before you do that, any questions about this? No? Okay. I can. I'll give you.
So did the length of the column change when it rotates?
No. The length of the column is now inclined. That stays the same. Over here, this vertical dimension, technically it's less than L, but if we're dealing with a small angle, L times the cosine of theta is equivalent to L. So it's approximately L. But if this starts to become nonlinear and the column starts to lean more and more, at some point you can no longer approximate that height as L.
I'm confused with the beta.
Yes.
So that's what is that?
Beta is the spring constant.
K.
Yeah, it's equivalent to the K value that you're familiar with for a linear spring. All right, we'll do an in-class assignment. Here we have a column with 2 springs, each of which has a spring constant K. Same K value, so 2 identical springs. And the dimensions are such that this is H, this is 2H, and that's H once again. It's a pin at the bottom. And the load applied is P. So if K takes on a value of 2 kips per inch and H equals 2 feet, determine the critical buckling load, or the load at which we'll say this is buckled. Yeah, let's go back and look at that example. I think I've made a mistake. So the question that I was asked is about this restoring moment. So the restoring moment should be the beta value, which is a constant, times the angle of rotation. So we don't need that length in there. So sorry about that. Should just be beta times theta, which means I can't cross out L from the other equation. Instead, L ends up in our final solution over L. So, and yeah, that makes total sense. So it should be a function of the length of that column, right? Because the longer your column is, as you'll see when we continue, is the more unstable, or the sooner it becomes unstable, the smaller load at which it becomes unstable. Thank you for catching that. Okay, so if we displace it like so, we're interested in these 3 deltas, delta 1, delta 2, delta 3. Delta 1 is equal to H times theta, 3H theta, 4H theta. Now we take the sum of our moments. Our disturbing moment is P times 4H theta. And the resisting moments are K times 3H theta times 3H minus K times H theta times H, and that has to equal 0. So if we plug in, we get P times 4H. Well, first of all, before I plug in, let me just point out that theta crosses out. And in fact, one of these H's crosses out. So that's what we're left with. So we have P times 4 minus 9 times K, which is 2, and H, which is 2. 9 times 4, that's 36, right? And then minus K, which is 2, times H, which is 2. So that's minus 4. That equals 0.
The H and K are in different units.
That's friendly. All right. What did I do? H is in feet. So we want H to be in inches? Okay, so it means that's not 36. That is 9 times 2 times 12. Is that what it is? So what's 24 times 9? 216. Cool. And then here we have 2 times 12, which is 24. So that should give us P equals 120 kips. Cool.